What happens when you get into the multi-core world? That's always been one of the hardest challenges in software development, simply because you're now writing for multiple cores. I think that started all the way back when we went into microkernels, where we had trying to run multiple applications on a single kernel. Now it's moved into the hardware where we're running it on multiple cores. Nobody's ever been able to compile that software.
Well, they are coming up with better techniques and new tools across the board. Multi-core is a huge trend in the industry, not just in servers, but as you've seen in consumer products. Things like the Cell broadband microprocessor that Sony uses in the PS3 is one example that I've been involved with. We're going to see more and more of that trend in embedded systems, where the systems on chips are going to be combinations of general purpose processors and accelerators. So essentially a very sophisticated multi-core processor that's going to support the differentiation in the products that these companies build. That's going to demand new technologies, new tools, and new methodologies to really successfully deliver those products to market in an economic and a time-efficient manner.
And Cell was only, 8 cores plus a hypervisor, whereas what we're talking about now in the future, what I've heard out of companies like Intel, is many, many cores.
Yes, I think you'll see in many cases, I don't want to state a number, but you're going to see a lot of cores, particularly for designs that involve high levels of integration, involving different types of workloads, where the accelerators help optimize the power, performance, cost trade-off that the engineers have to make in order to deliver their product to market.
Does it matter if the cores are homogeneous or heterogeneous? Is there a distinction there?
I think you're going to, there's not really an important differentiation there in terms of what's going to be developed. I see the market being a combination of both homogeneous cores, where you just replicate the same core multiple times, versus many of the embedded designs, you actually see more heterogeneous cores, where you have a specific general purpose processor coupled, again, with a accelerator optimized for a specific intended algorithm or workload that really, again, helps get the power, performance trade-off and cost trade-offs that the designers are trying to achieve.
Is it harder to write the software as we start moving down on different process nodes, say from 90 nanometers to all the way down to 22 nanometers?
The software development is independent of the node. What effect you have is, as you scale the technology, you can put more function on a chip of a given size. And so engineers are taking advantage of that to create more sophisticated and competitive products. And that complexity of function is what's driving the complexity and increase in the software development.
Just the ability to write more software onto a chip, and the more functionality that you can have there can delay it as well, right?
Absolutely. And what's becoming critically important in a number of markets is having hardware-software co-development. No longer can you really afford to wait until you have the hardware physically in hand to do your software development. The consumer markets move too fast, as one example. Consequently, many customers that I've talked with in my Power.org role in the past have said we have to solve that problem. And it's tools such as VAS that help solve that problem.
The world you're describing here sounds very eerily like the FPGA world and where they're moving.
Well, I think they both have a role, and they'll both continue to go forward to satisfy different needs. FPGAs satisfy a lot of needs in terms of development, but you'll still have more optimized systems on chip where the volume and the cost targets demand that type of approach. And when you have that kind of approach, it takes longer to get to the silicon. And therefore, having tools such as the VAS virtualization technology, that helps you get started on the software development much earlier in the development process. You don't have to wait and do it serially as in the past.
But your ability to upgrade the chip and change the chip and change the firmware sounds like the kind of stuff that you're building into the chip here.
Well, in terms of the model, you can clearly update it and change the model as you need to based on the engineering changes that happen. So it can keep up with the needs of the software development team that are going to be writing their code to the end hardware. But there's a lot of benefits of having a virtual prototype as opposed to a real prototype. Again, one is it takes long to get the hardware designed, debugged, into manufacture, and then typically you get a limited number of prototypes out, and those prototypes have to be brought up before the software team even sees it. If you can put up front in your design cycle the development of a virtual prototype, making a software model using the vast type of cycle accurate technology, then you essentially get all of that time back. While they're developing the hardware, you can actually start your software development. That includes the firmware, that includes the operating system changes that are required, or new operating systems if it's required for the application, and the actual customer end application that's going to be running on all of this.
That sounds like a huge advantage for a company such as a cell phone chip maker, which may say, okay, it's very expensive to build a chip. We're talking potentially $100 million for some of the advanced process nodes that are coming up. So they don't want to build it, but at the same time, they don't want to build it until they know that it's going to be used, but at the same time, they can't afford to miss the market window if it does open for them.
Well, one of the benefits of using a technology such as vast virtual prototypes, modeling and simulation capabilities, is that it gives you the capability for rapid prototyping in software without committing to the expensive hardware manufacturing to help you with the early sales. You can basically build a prototype, demonstrate it to your customers who are going to ultimately use that chip in their products. They can provide additional feedback, enhancing the product and making it more optimized for their end needs. So it really serves a very useful front-end purpose, so that the very expensive chip development process that we have, particularly as you scale down to these very fine nodes, we can basically have a more economic approach.
Mike Paczan, thank you very much for your time.
You're welcome. The embedded